Let's take the first number 14 to be inserted and take its hash value. For quadratic function I equals 0, the hash value computed equals to 3. Bin 3 of our hash table is empty, and we can insert into it. Once inserted, we will update bin 3 as occupied. Similarly, the second number 107, the hash value computed equals to 8. Bin 8 of our hash table is empty, and we can insert into it. Once inserted, we will update the bin 8 as occupied. The third number is 31. The hash value computed equals to 9. Bin 9 of our hash table is empty, and we insert into it. Again, once inserted, we will update the bin 9 as occupied. Thus, the first three numbers fall into bins 3, 8, and 9 respectively. Let's take the fourth number in our sequence of insertion, which is 118, and take its hash value. For number 118, the hash value computed for quadratic function variable I equals to 0 as 118 plus 0 squared, the whole term, mod 11, where 11 is your table size. The computed value equals 9, but bin 9 is occupied, that is, it's already taken by number 107, which causes a collision. Thus we further increment the quadratic function I equals 1 and compute the hash value as 118 plus 1 squared, the whole term mod 11, which equals 1. Bin 1 is unoccupied, therefore we insert into it. Let's take the fifth number in our sequence of insertions, which is number 34, and take its hash value. For number 34, the hash value computed for quadratic function I equals to 0 equals 1. But bin 1 is already occupied, that is, it's already taken by number 118, which causes a collision. Thus, we further increment the quadratic function I equals to 1 and compute the hash value, which equals to 2. Bin 2 is unoccupied, therefore we insert the number 34 into it. Let's take the sixth number in our sequence of insertions, which is number 112, and take its hash value. For number 112, the hash value computed for quadratic function I equals to 0 equals 2. But bin 2 is already occupied by number 34, which causes a collision. We further increment the quadratic function to I equals 1 and compute the hash value, which equals 3. Bin 3 is also occupied by number 14, which causes a collision. Thus, we further increment the quadratic function I equals to 2 and compute the hash value of it, which equals to 6. Bin 6 is unoccupied, therefore we insert into it. Now, in order to remove an element, we must simply mark it as deleted. In our example, let's remove the number 118, which is inserted in bin 1. For number 118, the hash value computed from quadratic function when I equals to 0 equals 8. Further incrementing the quadratic function, the variable I, to 1 and computing the hash value, which equals to 9. Again incrementing the quadratic function I equals to 2 and computing the hash value, which equals to 1. We go into bin 1, delete the item, and mark the bin as delete, thus having had an item deleted. So far, we have looked into inserts and deletes of quadratic probing. Now, to find or search an element, we start by checking the bin it should have initially been into. Basically, we will start from the location of the bin where the key originally hashed to. Then begin checking further, following quadratic probing, making a sequential search until either we find the bin which contains the key, and if found, it will be a success, or we find a bin which is empty, and in this case, it will be a failure. To find the element number 14, we start by checking the location of the bin it should have initially been hashed into. For number 14, the hash value computed for quadratic function I equals to 0 equals to 3. Thus, we find key 14, which is in bin 3, and it will be a success. Now, to find element number 34, we start by checking the location of the bin it should have initially been hashed into. For number 34, the hash value computed for quadratic function I equals to 0 equals to 1. But we find bin 1 marked as deleted. We further proceed by incrementing the quadratic function I equals 1 and compute the hash value, which equals to 2. Thus, we find key 34, which is in bin 2, and it will be a success. Further to deletions, let's take a number that was never inserted into our sequence of numbers. Let's pick number 19 and find it in the hash table by using quadratic probing approach. We start by checking the location of the bin the number should have initially been hashed into. For number 19, the hash value computed for quadratic function when variable I equals to 0 is 8. We find bin 8 in the hash table marked occupied, and the number the bin contains is 107. We further increment the quadratic function variable I to 1 and compute the hash value, which equals to 9. We find bin 9 in the hash table marked occupied, and the number the bin contains is 31. Further incrementing the quadratic function variable I to 2 and computing the hash value which equals to 1. We find bin 1 in the hash table marked delete. We further increment the quadratic function variable I to 3 and compute the hash value which equals to 6. We find bin 6 in the hash table marked occupied, and the number the bin contains is 112. Further incrementing the quadratic function variable I to 4 and computing the hash value which equals 2. We find bin 2 in the hash table marked occupied, and the number the bin contains is 34. Further incrementing the quadratic function variable I to 5 and compute the hash value which equals to 0. We find bin 0 in the hash table marked empty. In this case, it will be a failure. The sequential search breaks. This implies that the element does not exist in the hash table. Since linear probing is very easy to implement, its disadvantage is primary clustering, which is long sequences of unused bins build up with gaps between them. The phenomena of primary clustering will not occur with quadratic probing. Quadratic probing requires more computation power than linear probing, and it's not as simple and easy to implement as linear probing. Although primary clustering is avoided by using quadratic probing, since the probes are not sequential. However, if multiple keys or items all hash to the same initial bin, the same sequence of numbers will be followed for all the keys. Basically, if hash value of key 1 equals hash value of key 2, the probing sequence for key 1 and key 2 will be exactly the same. This is termed as secondary clustering. The effect of secondary clustering is less significant than that of primary clustering. What it implies here is that in practice, secondary clustering becomes an issue when your load factor is high, especially if it's above 0.5. This is because at most half of the table can be used as alternative locations to resolve collisions. Also, there is a theorem 5.1 in your book stating that if the table size is prime and load factor lambda is not larger than 0.5, all probes will be to different locations and an item can always be inserted. Secondary clustering may be a problem if the hash function does not produce an even distribution of entries. There exists techniques that eliminate secondary clustering, and the one that is most popular is double hashing. Double hashing will associate with each element an initial bin defined by one hash function and a skip defined by a second hash function. What implies here is that double hashing uses a second hash function when a collision occurs. The second hash function should never evaluate to zero. In essence, we resolve collision by choosing successive positions with a constant offset independent of prime hash value of the key. Basically, we jump stepwise away from the key's original hash value in constant step size, and that step size depends on the key value. For homework, go through the source files of quadratic probing provided in your lab code with some of the functions printed and explained in your book as well. The goal for this assignment is to gain experience, not only in understanding the code, but also to implement different examples using quadratic probing. You should understand in details the type defs, structures and function declarations as well as definitions in your hashquad.h and .c files of your lab code.